And the presentation is also okay, right? The sharing. I think so. Okay, then I'll get started. Thank you, everyone, to come today. And we need to sign that?
No, I'm just going to leave this because I don't want to slow you down.
Okay.
we'll maybe try it later.
Okay, thank you. Okay, yeah. So today I'm going to talk about quite different topic than my typical talk. Today I'm going to talk about generative design for embodied intelligence. So to start my talk, I want to just first focus on this term embodied intelligence, right? So to me, this word really highlights the fact that the ultimate intelligence that we as a field going after is not just a function of the brain, which is the computation part, but also the function of the mechanical structures of the robots, their sensing capabilities and their actuation capabilities as well, right? So all these other capabilities is actually provided by embodiments that is not in their software. And I think really the intertwined nature of all these different components make robotic systems such a hard system to design and optimize, right? So that is why robotics is so hard and we are not solving it yet. So how we typically approach it? I think the standard tactic for approaching a robotics design or robotic system is kind of doing this divide and conquer approach, right? So we have a very complicated system. We want to divide it into like different components, and we will focus on each of the components each time. And that's actually directly leads to the different specializations in robotics. So we have mechanical engineers who learns how to design the physical part of the robots. We also have CS people that's designing the software part. However, the problem is that this kind of job division not always lead to the optimal system. And more often than not, it actually leads to a lot of complaints from both sides. Right? So you can often see there's complaints from like the software people kind of complain that your hardware is not precise enough. And then the hardware people kind of just say that, no, my hardware is precise, it's just your controller sucks. And then I guess on the other stream of the spectrum, what we can hope for is that we can have this one expert that knows all the tools and knowledge of hardware and software, and that's everything, and there's no problems at all. But of course, this is not very realistic, right? So if we require all the robotics PhD to understand all the tools and knowledge in robotics, then they will take forever to graduate. So what is a more realistic approach? I think what we really need to work on as a field is trying to make this hardware design process much simpler instead of much harder. Right? So how we can make it simpler? I think one idea is that can we try to simplify all the tools that we use by kind of unify it into one single tool, and then as a result, the engineers only need to learn that one tool. And then by using this unified tool, we can automate and simplify the whole design process. Well, as you can guess it's I think one of the good guess is using machine learning as a tool to optimize both software and hardware design. So we already see a lot of progress and success in how to use machine learning to optimize the programming part of the robot. Right nowadays, it's much easier to make a robot to do a new task through machine learning. The robot will be able to learn. And that is much simpler compared to the classical ways of doing it, is writing the explicit program. So the question now is, can we apply similar idea that's to hardware design? So also here, I want to make a disclaimer is I don't think that we are there yet. We are very, very far, right? So I think machine learning cannot replace like majority of the tools in the mechanical design. But I think it's a really good time to start to think about it, because fundamentally, what machine learning provides us is actually two very powerful capabilities. First is that it gives us the ability to try to distill knowledge from large amount of data. Right? So this data actually can be robust sensory motor skills or sensory motor experience. That's when we're learning the robot policy. And at the same time, the data can be a lot of good and bad hardware designs coming from, for example, simulators. And the second capability is that machine learning actually provides us a way to automatically optimize a lot of parameters of the system. Right? So what are those parameters? It could be the action parameters, which again is a typical policy learning, but it could also be the parameters for the robot hardware configurations. Right? So if you think about it, there's a lot of parallels in this two problem, and potentially the machine learning method can be applied for hardware as well. So with that kind of idea, we can potentially start a new paradigm for robot design, where the engineer will just need to define the objective, what I want the robot to do, like the task objective, and kind of roughly sketch out the design space for the robot. And then the robots or the machines will be able to automatically optimize its configurations, like their parameters in both their action and hardware, in order to give you an optimal system. Right, so that will be a really nice paradigm to reach. So today I'm trying to ground this very big grand vision or like big idea into a very concrete example. We're going to talk about this very specific task of trying to use machine learning for robot manufacturing design. Right, so this is the focus for today's talk. We'll do a case study on whether it is possible. Okay, so first you may ask why we care about robot manufacturing design. There's so many parts of robots. Why we just focus on manufacturers? Well, I think if you think about it carefully, the robot's manufacturer, which is their hand, is really the physical interface that is interacting between the robot itself and its environment, right? So as a result, this interface design really critically determines the robot's overall performance and its functionality. Therefore, if you tweak it a little bit, or if you design it better, you can drastically impact the performance of the system. So here is just a quick example from our past work. So here to highlight the importance of manufacturing design. So in many of my past work that I work with Jimmy, we actually use a very simple robot. This is called an Anki robot. So it can move around, but for its hand, it only has one lever of actuation. So it can only rotate this one link. But we use this robot to do many different things by changing the end effector shape. Right? So actually, if you just 3D print a different mount on the end of the robot, this robot can actually lift up the cube, can push the cube, can like toss the cube backwards. And if you put the end effector as a little fan, you can even blow airs and like clean up leaves. So this example really, what I'm trying to show you here is that even with a very simple robot, if you carefully design an end effector, the robot can do a lot more than we think. So the importance of end effector design. And also, I think similarly in industry applications, if you actually go to most any of those automation industry or like actually assembly lines, you will see that almost all the assembly lines use task-specific design of their end effectors. They will design their hands or their gripper for the task or the objects they are manipulating with. Right. So obviously, there's a lot of benefit from doing that. First is that you can easily improve the performance for the task you care about. And also it can drastically improve the robustness of the system because it simplifies the system, right? So in the end, actually, if you're able to design the correct end effector, you can make the system even don't rely on vision. So that's why it can make the system a lot more robust. And also, this type of design is relatively easy to deploy. You just need to switch out the finger geometry, and then you can actually change the same gripper to do different tasks. And they can do it very reliably. But the downside for this kind of task-specific design is that you often require a lot of engineering experience to come up with the right design and tweaking the right design so that it works in all the scenarios. So as a result, oftentimes you only see this kind of tailored or customized end effector design in large-scale manufacturing, which is more cost-effective. So the question now is can we automate this end effector design process with machine learning? And then to answer this question, I'll talk to work done in the past that is focused on using machine learning for end effector design. And then first, I will talk about the work of Fit to Form, which is done by my student Lee, and also this the gripper design for grasping of objects. So we form input of this system is a target object we want the system to grasp, and the output of this will be the finger shapes for a parallel gripper. We do not change the kinematic structure of this gripper. We only change the shape of the gripper. And then the objective is that we want the designed end effector shape able to reliably grasp objects, which is the typical grasp success rate that you want to measure. If you close the gripper, able to grasp object. And in addition to that, we also want to make sure that the grasp is stable, right? So we want also to evaluate that, we'll apply external forces on the grasp object and measure whether the object will still be within the gripper. So this is very important. We will actually apply it in a real application. And then the third of the grasp will rotate or switch or like translate the target object in this 2D plane, your gripper should still be able to grasp the object. So this is actually particularly important to handle precision errors in post estimation, right? If your target object is not guaranteed to be always in the perfect pose, then this kind of robustness is very useful. You can always able to grasp this object. So this is the design objective that we want to achieve for the gripper that we designed. And then also we want to make sure that the design, the output of this gripper design is manufacturable, right? We can 3D print these grippers. So we want to add printable is a one connected component and is connected to base. So those are the manufacturing constraints. Here I'm going to talk a little bit about high-level approach for how we're able to achieve that. On a very high level, the approach actually composed of two parts. One part is a generative network that is trying to help us to navigate the large design space, and the other part is trying to use a neural network to represent the high-level design objective. In this case, is all the objectives that I talked about, like about grasp size or stability and robustness. So how to do that? For the first part, we actually use a 3D generative network that help us to generate 3D shape geometries given a target object. Right? So this generative network is basically a 3D neural network that giving a target object will generate 3D geometries of each of the fingers. And here the geometry is represented in voxels. So we make this decision back then is we want to make sure that the robot or the machine learning algorithm has all the degree of freedom that they have to come up with new designs. We don't want to just parameterize them as primitives and then only do local adjustments. We want them to have all the degree of freedom to optimize a 3D shape as a voxel. And on the other, to represent the high-level design objective, we actually trained a fitness network that's taking the geometry that's generated by the generative network, and then the target objects, and then directly predict the evaluation metrics that we care about that I introduced earlier. Right? So for example, task success rate, stability, and robustness. And then we can get the labels for all this evaluation metrics directly in simulation. We can simulate the grasp success in simulation, and we train a neural network to approximate those metrics. So you can see that here is basically a very similar idea in the previous talk. That's a surrogate model that we basically try to train this fitness network that's try to learn a differentiable approximation for those non-differentiable simulators, so that we can get the gradient from this neural network. And then once we have this two neural network, the optimization is actually quite simple because both network is differentiable, and then the generative network is trying to train to maximize the fitness network's output. And then you can actually train this end-to-end together with these two neural networks. And then here I want to just quickly show you some of the design that's generated by the network. And then we actually 3D printed and tested in the real world with the real world objects. So here we actually, in particular, test on objects that's very hard to grasp. So I think back then there is a paper that's from Ken Gober's group. They generate a set of like adversary objects that is very hard for typical gripper to grasp. So we actually test on those objects for the generative grippers. And then we also try to do some comparisons with some reasonable baselines, right? So here we compare with two baselines. One is the original design for this WS350 gripper. That is the same geometry. And then we also compared with another baseline that is called imprint gripper. So this imprint gripper is actually a very typical or standard way people actually in industry that's designing task-specific or object-specific gripper. It's basically just use the inverted shape of your target object, right? So this is actually very, it feels intuitively a good idea, but in reality, it's actually quite hard to make it work well because this kind of design is very sensitive to misalignments of the object. Therefore, it's not very robust to any like perception errors. And then you will see the issues later in the. So we run a lot of real simulation and the real world, and here is aggregated result and comparison. So you can see that the generative network is indeed able to generate better designs for grasping those adversary objects. And in particular, I think they are better in terms of the stability and the robustness. Right? So, but if you want to answer the question why those designs are better, we need to actually look at the particular designs. So here is, I'm going to show you a few of those typical designs that this network, or like typical strategies that the network actually figured out to use in order to improve their performance. So one category of this emerging design that we observed quite a lot in the network is what we call a single-sided screw. So this name is a little less scientific, but the idea is that if you observe the generation, the finger actually has a flat surface on one of the finger, and then has a hollow surface on the other side, right? So it's actually very unsymmetrical. And then in the end, when the gripper is trying to grasp the object, basically the flat surface is pushing the object into the cavities in order to grasp the object. So you can see that what the network learned is actually to use the flat surface to kind of help to reduce uncertainties for the grasping dynamic flow to generate the right shape to perform the form closure. So this is one typical design. And also if you look at objects that's bigger in size, you will see that the generative design actually has bigger space for those bigger objects. It's no longer flat on one side. And also, we observe that for those when the robot is presented with bigger objects, they also turn to generate those structures on the side of the gripper in order to improve the stability of the grasp. And then, and third category of design that we found very interesting is that the network will actually learn to generate some kind of protruding structure that try to dynamically hook up the objects during the grasping process. Right? So in this process, actually, it's no longer just considering the static form closure when you're just considering the object geometry. It actually does take into account of the whole grasping process, which is quite different strategy compared to the earlier two. So that is the kind of like quick summary for fit to form. And then if you think about it, it's a very simple system that's dealing with a very simple task. And of course, it has a lot of limitations. Right? So first, I think one of the biggest unsatisfactory part is that the task that we're dealing with is quite simple. Right? We only consider a single task, which is grasping objects. And also, for this particular task, as you can imagine, it's not too hard for a human designer or engineer to come up with a better design. Right? Maybe a few iterations will get you there. So a natural question to ask is that, can we use a similar method, but tackle a task that's much harder to design, like much harder for human engineers to come up with? And another very obvious limitation that's kind of we figured out in the middle of this project is that the voxel-based representation, although we give a lot of freedom for the network to generate creative and new design, is actually really costly and it's not optimization friendly. And so it makes the design space extremely high dimensional and make it extremely hard to navigate. So there must be some better 3D geometry representation that is better, that still have the degree of freedom to optimize, but also easier for the optimization outcome. That is like two big limitations or issues I have with this work. So 4 years later, we actually have a follow-up work that's trying to improve both of those issues with a new, very different method. So this is called dynamic guided diffusion model for robot manipulator design. And this is actually done by Salmon, who is the organizer, and it took us 4 years to come up with the second design. Okay, so here is the task that we considered in this project. So this is one of the tasks we consider. It's called convergence. So what this task do is that given any target objects that, like for example, in this case is a T, regardless of how you put down the object, what kind of pose you put down the object, after the robot squeezes the gripper multiple times, it will automatically align to a target pose. Right, so this is the task called convergence. As you can imagine, this task can be very useful in your assembly line because when your objects are coming in with different poses, after this a few squeezing actions, you'll get all the objects aligned in the same pose. Very practical application in industry. And oftentimes people call it fixtures or other things that basically achieving the same goal. So although this is very useful, but as you can imagine, it's And also if you are able to achieve this goal, your follow downstream task where the robot system can basically just randomly pick up the object, do not need to even do any pose estimation because we already know the pose. So this task is useful. However, it's actually really hard or counterintuitive to come up with the right design. Right? So if you just ask yourself this question that's given a target object, what is the finger shape for the convergence task? I don't think you have a good intuition of how to design it. Right? So it does take a very experienced engineer many days or months to come up with a good design, or if ever come up with a good design. So in this project, we actually in particular pick this task that is hard enough and also useful enough for us to study. And then, yeah, so the goal is to automate the whole design process with a neural network. So the high-level idea for the approach is actually very similar to the earlier feed-to-form project. We still have a generator that helps us to represent the distribution of shapes. We also have an evaluator that helps us to evaluate whether the design is good. But the actual implementation for each neural network is very different this time. So for the generator network, this time we actually made two major changes. One is that we changed the geometry representation from the voxel to a set of 3D control points, right? So it's drastically reduced the dimension or the dimension we need to optimize for, but still provide enough flexibility for optimizing any geometries. And then another difference is that now we actually, instead of training just a feed-forward convolutional neural network as a generative network, we actually trained the generative network as a diffusion model. So that we know that for diffusion model, it's actually particularly good modeling many like this complex multimodal distribution, which is very good for this design problem because it's very natural to have those complex multimodal distribution appeared in your design space. So having a model that's able to capture multiple modes is very critical for the generator. And then, so that is the generator network. And then for the evaluator that try to evaluate whether your design is good or not, this time we actually try to make this more this evaluator more general. We no longer want it to be overfit to one particular task. We want this evaluator to be able to work for many different tasks. So the idea for us to do that is we actually trained a dynamics network that is learned to predict the dynamics effect of the interaction. And then after that, we can actually use the same dynamics network to represent many different design objectives. Right? So we're going to break down how we do that in a bit. So first, let's understand what is this dynamics network. So this dynamics network is trying to predict interaction profile. What's the interaction profile? So this is basically an expected delta post after interactions. So give you a very simple example, like say the very earlier example that's given a target object. Let's say that it has an initial post, which is corresponding to the x-axis for this profile. And then after one interaction, the object post will change, and that will give us the corresponding delta post change on this profile. And then if you sample different initial posts, you'll be able to get a complete interaction profile for this particular object and also this particular pair of manipulators, right? So after you generate a lot of data in simulation, this dynamics network basically can predict, given this object and this manipulator, how this object will move after interacting with it. So here I visualize it in just one dimension, but in reality, the interaction profile is actually high dimension. It represents both the rotation and also translation. Okay, so that is the interaction profile. And then how we use it to construct different task objectives. So here, again, is this convergence task. If we want the model, if we want the system to able to generate paper for this convergence task, what we really want is basically, let's say that we select the target post, which is the theta target. And then if the initial post of this object is smaller than theta, we want it to rotate clockwise. And if the initial post is larger, then we want it to rotate counterclockwise. Right? So this design objective can actually be easily expressed with a target interaction profile like this. And then if you compare these two interaction profile with the predicted and the target, it will give you the difference and also the gradient for you to optimize the gripper geometry. Right? So that's how we're able to use the same dynamics network to construct different target tasks. Okay, so when we combine these two things together, we basically have a dynamic scattered diffusion model. And then we can use the gradient generated by the dynamics network to guide the denoising process and using basically just very similar to classifier-based guidance for the diffusion network. And then here again, this dynamics network is basically our differentiable approximation for a non-differentiable simulator. But this time we'll make it more general so that it can be actually reused to construct different design objectives. So yeah, we can use the same model, but both the generator and the dynamics network for many different design objectives. So here is just a quick overview for the different tasks we test on. So you can design the gripper that's always shift up the object, shift down, right, left, rotate clockwise or counterclockwise. So these are all the different. So basically, as long as you can write the target interaction profile, you can use the same network to generate the gripper design. So just a quick overview. I talked about two of those works that both are focused on generating robot grippers. And if you look at these two work in a high level, you actually can see that the role of learning algorithm is actually very similar. So first, the learning algorithm help us to summarize the design space into a generator network. And the second is that the learning algorithm is actually really, really helpful to help us represent the design objectives. That's the differentiable function. In the first case, we represent it as a fitness function that is task specific. And in the second case, we represent as a dynamics function that is actually can be shared and reused for different tasks. Okay, so that's for end effector design. In the remaining few minutes, I want to talk a little bit about what we want to do next or how we can go beyond just end effector or robot end effector design. So I spent a lot of time talking about the robot hand, which is actually quite a small part of the robot. Right, so if you think about a mobile robot, it comes with its arm, its mobile base, it has a lot of other components, which really motivates the idea of trying to do a whole body optimization, consider all the degree of freedoms of the robots altogether. So I think it's probably most obvious to apply those ideas in those complicated robots like humanoids or quadrupeds. But what I want to highlight today is that even if you have a very simple system, considering design optimization for your hardware still matters. Right? So I think many of you probably has used some kind of bimanual setup, like this is Aloha design, and many of you probably directly download the Aloha design and try to reconstruct it in your lab, and it probably work very well. But have you thought about if you just simply change the mounting positions or the mounting orientations of this to improve the performance of the task? Actually, it's not very natural to do it with the horizontal mounting pose. If you change the mounting pose directly a little bit, it actually can improve the performance quite a bit. And then similarly, how about each individual arm designs kinematics, right? So what if you make some of the link longer or shorter? What if you increase or decrease a degree of freedoms? And I think more interesting question is that does the design need to be actually symmetrical? I think most of the bimanual design is symmetrical, but does it always need to be? My answer is that, oops. My answer is probably not, because if you think about all the tasks that we do, we ask the robot to do, most of the tasks is actually not asymmetrical. And also, if you think about the learning from demonstration paradigm, most of people has a dominant hand, and then the way the trajectory complexity that you demonstrated is actually quite different on left and right, right? So why we need to make the robot hardware symmetrical? So I think this is a symmetrical design is very easy to think about, but oftentimes it's not really optimized for the particular task. So that's its whole body optimization. Another interesting aspect or like a venue that I think we can think about for learning for design, or just in general think about better design hardware is sensor designs, right? So we know that in nature, actually animals, depends on whether you're prey or predator, you actually optimize your eye locations for either hide away from the predators or try to have better depth vision. And similarly for robots, if you design the robot for doing very different tasks, like a process insertion task or a navigation or searching task, the way that you will mount the camera will be very different, right? So if you ever design a big robot system for a new task, I think the first question you need to answer, and it's also a tricky question to answer, is where to place your sensor, where to place your camera. And that's actually very critically impacting your system. So taking this idea, one of our recent work is called Vision in Action. We actually designed this active robot neck stuff. It can actually move around during this manipulation process so that it can actively optimize the correct camera pose or the better camera pose during different part of the manipulation stage. Right? So that you don't need to predefine the camera mounting locations at the beginning, but instead you can actually optimize or learn the proper camera placement in the process. And then also, if you take this idea one step further, why stop at one camera when you can just install so many different cameras on the robot? So actually today, cameras are very, very cheap. You can get a good camera, $6. And in this project, we actually installed 21 cameras on this very little robot. And then because of all these cameras, we allow the robot to actually have the whole body vision, and then really enable some new capabilities like whole body sweeping, and or like the kind of examples of getting into very narrow space, like opening this box. If you imagine any other camera placement, like a camera on the ceiling or a camera on the side, you will not be able to do this task. But if you add just many more cameras, you are able to do this task a lot better. So this project is called Robot Panoptis, and that means many eyes on a robot. Okay, so this is my last slide. I want to summarize basically what I'm talking about today. Is I wish you, as a field, really think about the opportunities and the challenges of how to apply machine learning for embodiment design or hardware design for robots. Right, so I think the key takeaway I want you guys to get from this talk is that as a field, we probably should think about how to move away from this very narrow paradigm that we just keep thinking about how to design different learning policies or learning different policy on a fixed robot hardware, to a new paradigm that we really treat the hardware part or the embodiment part of the robot as an integral part of their behaviors. So as a result, we can make the robot system a lot more adaptable to different environments, resilient to potential embodiment damage or changes, and also more versatile to different tasks. And I always like Transformer as an example for this idea, because this is actually a perfect example to show that this robot is actively changing its embodiment geometry to adapt for different tasks and scenarios. And I hope that our robot can be just like that. And that's the end of my talk. Thank you.
Thank you, Shuran, for the wonderful talk. I think we have time for just one question. Can we do it over there and others will be for the
as you know, any vector design engineer, the thing in vector design with the specific task or the reality is more.
Yeah, so I think the question is about whether we want to have specialist hardware design or we really want like a generalist hardware design. My answer is that general design will probably be more cost effective because it will give you one design, try to adapt to many tasks. But if you really want best performance, task-specific design is always give you better performance. It's kind of like you will think about consumer products. You always have the product that's able to satisfy 80% of people's needs, but the best product for the things that you really care about, you want to personalize it, customize it, and that is the way that you can squeeze out all the performance and make this potentially make the system even more robust. Yeah.
Thank you. We will move to the lightning talk. Thank you, Shuran, for the great talk.